You know, a lot of the motion that we've been talking about in physics has been motion in a straight line. Well, sure, we've had projectile motion, but have we had motion like this? That's a roulette wheel, and of course it's spinning in a circle around an axis. There's a point in the middle of it, right around there, that isn't moving, and the points that as you get further away are moving faster and faster and faster. So that point in the middle that's not moving is kind of called the axis. But there's another kind of thing that also involves rotational motion, and it's this, a door closing? Well, sure. If you imagine the hinges as the center of a circle, then the door is moving in a circular path, or at least all points on the door except on the axis, that is the hinges, are moving in a circular path. And so it's time to discuss rotational motion. And we can't discuss rotational motion without discussing angles, of course. And so we're going to start with a circle with on some x and y axes like we usually have. And that little vector there, or arrow, we'll just call it an arrow, is at an angle that we'll call theta away from the positive x-axis. Positive angles, as you know, rotate around in this direction. Negative angles this way. S we'll call the arc length, and r is the radius of the circle. Now, as it turns out, there's a pretty neat relationship there. As you can probably see, if the angle gets bigger while the radius stays the same, the arc length will also get bigger. In fact, if you think of this as a rotating arrow, as it's moving, the arc length that is swept out is getting bigger and bigger at exactly the same rate that the angle is getting bigger. Now, what do I mean by the same rate? Well, if you double the angle, you'll double the length of this arc. Make sense? So how do we compare the two? Well, one nice way of doing it is by measuring the angle in what are called radians. If we use what's called radian measure, then we can simply say that the arc length is equal to the radius times the angle. Make either the radius or the angle bigger, and you'll make the arc length bigger. Make sense? So there's a direct proportionality there. It's very nice and a very clean way. Now, the warning is the angle will be not in degrees, which most people are used to, but in some other unit that's actually defined by that equation. In fact, the unit of the radian isn't really a unit. And what I mean by that is it doesn't take part in any computations like, say, meters or seconds would. Okay, so it actually simplifies things. It's so natural that in certain calculations, it vanishes. Heck, look in this very equation right here. If S is an arc length, it would be measured in meters. R is a radius, so it's also a distance, so it's measured in meters, which means meters equals meters. That leaves nothing for the angle to be measured in. You might say radian is meters per meter, so it cancels out. Okay? Worth noting, since the circumference of a circle, as you all know, is 2 pi times the radius, right? 2 pi r, or pi times the diameter. That means that if the radius is 1, the circumference is exactly 2 pi. But if the radius is 1, the arc length and the angle are the same. So that means that the arc length is also 2 pi. Okay? So if the radius is 1, the arc length for the entire circle would be 2 pi, but that would be precisely the angle measured in radians. But we already know that the angle around a circle is 360 degrees. So if we divide both sides by 2, we find that pi radians is 180 degrees. And that gives us a nice conversion factor between degrees and radians, because that means if I write something like pi divided by 180 degrees, and don't forget about your little circle right there, or if I write 180 degrees divided by pi radians, those are both the same thing. They are the number 1, because anything divided by itself is the number 1. So it gives you a nice little conversion factor to compare degrees and radians. Okay, so for example, 90 degrees is pi over 2 radians, 45 degrees is pi over 4 radians. 30 degrees is pi over 6 radians because it's 180 divided by 6, so it's pi divided by 6. See? So pi over 6 radians is 30 degrees. All right, so enough of the math stuff. Let's keep talking about physics. S is called the displacement. Now it's along a circular path, so it's not delta x anymore. In fact, we could call it delta s if you wanted to. Delta theta is called the angular displacement. So this would imply that the angular speed, that's average angular speed, that little Greek letter right there, by the way, has a name that's called omega. The average angular speed is just the displacement divided by the time, the angular displacement divided by time. You notice how similar that is to our linear motions? Didn't we say v is delta x divided by t? That is, velocity is displacement divided by time? Well, average angular speed is angular displacement divided by time. Okay? Naturally, of course, its unit would be in radians per second. Now, since a radian isn't really a unit, we could also just call it an inverse second, and that works fine. By the way, the radian per second is not the only possible unit. You could have it in degrees per second, or revolutions per second, or revolutions per minute. It's just this is the most common and easiest one to use, radians per second, because then the radians go away. So let's try a problem. A record player rotates at 33 1/3 revolutions per minute. A record player, by the way, is one of those things for you kids out there. What would that be in radians per second? All right, let's try it. Let's write it all down here. Let's see, at 33 1/3, that's 100 thirds revolutions per minute, also called RPM, which was a rock group of the 90s. Let's convert that. So I'll leave some space. We're going to convert that to radians per second. So I need conversion units that'll cancel out revolutions and minutes and put in radians and seconds. So let's try this. Let's start with the revolutions. Well, we know that one revolution is 2 pi radians. 2 pi to get around a circle, right? And I put the revolutions on the bottom so that they will cancel. And we also know that 1 minute is 60 seconds. Put the minutes on the top to make sure that those cancel. And sure enough, we're going to end up with radians per second. So we've got our unit right. Now it's just a matter of computation. Well, we can do a little bit of canceling here. Let's see. 2 cancels 60, leaving 30. 100 cancels 30 by dividing them both by 10, leaving a 10 up here and a 3 down here. And we've got a pi right there. So it's going to be 10 pi divided by 9 radians per second. And that's a good math class kind of answer. What about here in the physics world? Well, in the physics world, we compute things. And when we compute that, we get a nice answer of 0.349 radians per second. You know what? I'm just going to write it as inverse seconds. That's our answer. Okay. So easy enough to compute. Got it? Okay. We move on. So let's talk about angular acceleration. Well, let's see. In the linear world, isn't acceleration the rate at which velocity changes? That is, change in velocity divided by time. Well, then angular acceleration would be the rate at which the angular velocity is changing. And angular velocity is omega. And so the rate at which angular speed changes, let's see, what Greek letter is that? Well, we all know that one. That's the famous alpha. Alpha is the Greek version of a, so a for acceleration, is the change in angular velocity divided by time. And so that's what we would call the average angular acceleration. That's what the little bar on top means. So we would compute that by finding the change in the angular speed and dividing by how much time that change takes. What about its unit? Well, the angular speed is in radians per second and time is in seconds. So the unit of this is going to be radians per second squared. But remember, radian isn't really a unit, so we can just call it inverse seconds squared, or seconds to the -2 power. Any questions? Oh, wait, this is a video. You can't ask questions. At least I can't answer them directly. I'll try to anticipate what your questions might be. Yeah, this could be in degrees per minute per hour. All you need is a unit of angle on the top and 2 units of time on the bottom. And they don't even have to be the same unit. But this is the most common one. So when the old record player that we talked about before is turned off, the disk rotation stops in 25 seconds. What is its average angular acceleration? Well, let's take a look. First, why don't we list some variables? Okay. The initial angular speed was 33.33 revolutions per minute, but you know what I'm going to do? I'm going to put back our answer that we found the other time, 0.349 radians per second. The final angular velocity is 0 because it stops and the time is 25 seconds. So we don't know if it all happened at a constant rate. So I'm going to put the little bar on top here. So it's going to be final minus initial. So 0 minus 0.349 divided by 25. And we get 0.014 radians per second squared. Well, actually we don't. We get negative 0.014 radians per second squared. So the forward direction is not the direction that it's accelerating. It's accelerating in the negative or clockwise direction. And so it's slowing down. Okay. Actually, let's go back to that video. It's actually rotating as we view it from above in the clockwise direction. So that's positive for our particular problem. So that means that it's actually accelerating in the opposite of the clockwise direction. So that'd be the counterclockwise direction. That's uncommon. Usually we use counterclockwise as our positive direction, but that's not the way the record rotates. What about all of these formulas? Well, I want you to notice how similar they are to the formulas that we had for linear motion. Remember how we had, for example, that final velocity is equal to initial velocity plus acceleration times time for linear motion? Well, for angular motion, its final angular velocity is initial angular velocity plus angular acceleration times time. This was in the linear motion 2a delta x equals v final squared minus v initial squared, and so on. All of these are the same formulas that we had for linear motion, except they've been transported into the rotational world. So, for example, instead of delta x, we have delta theta. Instead of v, we have omega. And instead of a, we have alpha. T is the same because time doesn't rotate. Clocks rotate, but time doesn't rotate. It's a scalar. These are actually vectors. We'll discuss that at some other point. And so if you know all of the formulas for linear motion, you have the formulas for rotational motion as well. So let's try a problem here. A disk starts from rest and accelerates at 12 radians per second squared for 6.7 seconds. Through what angle did it rotate? Well, the best way to approach this, I think, is the way we've been doing it all along, and that is to list our variables first. So the initial angular speed, you have to get used to what these variables mean, is 0. It starts from rest, so right there. And it accelerates at 12 radians per second squared, that's alpha, for a time of 6.7 seconds. There we have it. Through what angle did it rotate? Well, we need to find a formula that involves all of those variables. And here we are. The angle through which it rotates would be delta theta equals initial angular velocity plus 1/2 times time plus 1/2 acceleration times time squared. Better have the formula right. And so we can just plug numbers into that. It's going to be 0 times 6.7 plus 1/2 times 12 times 6.7 squared. And then we compute the answer, and we're done. My calculator says that the answer is 40.2, but that's too many significant figures, so we're going to round that to 40. I'm going to put a decimal point there to show that we do have 2 significant figures, not just 1. Now, what unit is that going to be in? Well, this is in radians per second squared. This is in seconds, but we're squaring it. So the seconds squared cancel. Our answer is 40 radians. That's the angle through which it rotated. Got that? Okay. And if you want to find out how many revolutions that was, you divide it by 2 pi. And you can see how many times the disk rotated during those 6.7 seconds. Okay. What I want you to get across is that at least mathematically, your work with rotation is very similar to the work that you do with linear motion. Similar equations, similar setup. We draw pictures, we list variables, we use formulas. That's all there is to it. Good luck with this, and I'll have more for you coming up.